Good morning. Today I would like to explain about the determination of modulus of rigidity of the material of a wire by using Maxwell's needle. So heading is to determine the modulus of rigidity of a wire using Maxwell's needle. Okay, so we have to take Maxwell's needle like this. It is hollow cylindrical tube in which other four tips can be inserted. This is the metallic wire whose modulus of elasticity is to be determined. Okay, we have to place inserted solid cylinder. There are four cylinders. Out of them, two are solid cylinder and the rest two are hollow cylinder. The hollow cylinder are kept near the axis of rotation. This is S represents hollow cylinder, S represents solid cylinder. They are equal in length. If this total length of the wire is denoted by L, then length of each cylinder is L by 4. Okay, L by 4. Let us suppose this one is L dash. Semi length of Maxwell's needle L dash. Then time period torsional oscillation. If it is given a jerk like this, it oscillates to and fro. We measure the time period for 20 oscillation and calculate for one oscillation, time period for one oscillation. By theory, T1 is equal to 2 pi under root, T is equal to 2 pi under root I by C, I1 by C. Here I1 is the moment of inertia when solid cylinders are kept outside and hollow cylinders are kept inside near the wire, okay, experimental wire. This is point of support, this is point of oscillation. In about the vertical plane, it oscillates like this, okay, clockwise, anti-clockwise. Squaring on both sides, T1 square is equal to 4 pi square I1 by C. Equation 1, where C is the restoring torque per unit twist. Now in second figure, this is figure number 1. In second figure, we have to measure the time by keeping the solid cylinder near the axis of rotation, that is to the experimental wire solid cylinder. And then hollow cylinder are placed. Hollow cylinders are placed like this. Okay, this is rotation. This is point of support. This is point of oscillation. This is figure 2. Let T to be the time period. Then time period for the second case is 2 pi under root I2 by C. I2 is the moment of inertia in this condition. Squaring on both sides, T2 square is equal to 4 pi square I2 by C. This is equation number 2. Now here in the first case, the solid cylinder are kept outside, okay, like this. So the moment of inertia by formula I is equal to mk square. Mass distribution is away from the axis of rotation. Therefore, moment of inertia is high. Radius of gyration is high. It means time period is also high in first case. Therefore, we subtract second equation from 1. T1 square minus T2 square is equal to 4 pi square I1 minus I2 divided by C. Equation 3. But modulus of this restoring torque per unit to C is related by the expression pi eta R4 by twice L. Here this small L is distance from the support to the center of this Maxwell's needle. Considering this one is point mass, C is equal to pi eta R4 by twice L, where eta is modulus of rigidity, R is radius of this material of this wire, L is the length of this wire, R is the radius, L is the length, N is the modulus of rigidity, C is the restoring torque per unit twist. Likewise, moment of inertia I1 minus I2 can be written as mass of solid cylinder minus mass of hollow cylinder times L dash square. Here L dash square is distance from axis of rotation, that is from the wire to the extreme end. Okay, actually this is L dash is L by 2, 50% of this one. Substituting this equation of C from equation 4 and 5 into equation 3rd, what do you get? T1 square minus T2 square is equal to 4 pi square. I1 minus I2 is mass of solid cylinder minus mass of hollow cylinder, L dash square divided by C is pi eta R4 upon twice L. This pi and pi cancel. This is equal to 4 to the 8 pi L, small l, mass of solid cylinder, mass of hollow cylinder, L dash square divided by eta R4, T1 square minus T2 square. Here modulus of rigidity of the material of the wire is equal to 8 pi L, mass of solid cylinder, mass of hollow cylinder, L dash square divided by T1 square minus T2 square times R to the power 4. Here L dash is actually L by 2. L is length of the Maxwell's needle here to here, right? From here to here, total length. It is generally equal to 30 centimeter, but we have to measure in lab. It depends on Maxwell's needle quality and its nature. Okay, so 30 centimeter. Thus you have to determine the modulus of rigidity. You have to convert this L dash into total length of Maxwell needle, 8 pi L, small l length of wire, mass of cylinder, mass of hollow cylinder times L square by 4. If you square it on both sides, you will get L dash square is equal to L square by 4. T1 square minus T2 square times R4. This 4 to the 8, 2 pi small l, mass of solid cylinder, mass of hollow cylinder time length of Maxwell needle divided by T1 square minus T2 square times R4. Thus, knowing all these quantities, you can find out the value of modulus of rigidity of the material of a wire. Okay, it is up to 10 to the power 10 Newton per meter square, and depending upon the nature of the wire. Thank you for watching.